Hi. Welcome everyone to this evening's PyData Riyadh meetup. Thank you all for attending. Just a brief introduction about PyData. PyData is a program by NumFOCUS, and it's focused to bring a community to anyone who's interested or developing a data analyst related tool or project, and it's aimed to anyone in general who's interested in Python and data. This PyData chapter in Riyadh is organized by Abdulrahman Alfozan, Daniel Dosri, Ruba Al-Marrouti, and myself, Abdulrahman Alfozan. And this evening, we have Abdulrahman Alfozan with us. Abdulrahman is a system engineer at Facebook, and he's a contributor to the Apache Spark project. Abdulrahman is going to talk about MLflow, an open source machine learning lifecycle platform. It's worth noting that this talk is going to be around 50 minutes and followed by 10 minutes for Q&A. Please use the Q&A functionality on Zoom to submit your questions, and we'll get to them at the end of the talk. And once again, thank you all for attending. Off to you, Abdulrahman.
All right, thank you. Thank you, Abdullah. Let's become the host. All right, well, assalamu alaikum, everyone, and good morning or evening, depending on where you are. I'm currently based in California, so it's 11 in the morning. It's good to talk to all of you. I hope, inshallah, this will be a productive workshop or session, and looking forward to hearing your questions at the end, inshallah. So let me share my screen. So we have slides and a demo. We're gonna split this presentation or this workshop between the two. All right, let me. Just 1 second. Yes, 1 second until I share my screen. All right, try again. All right, I guess now we can, I'm hoping everyone can see the screen. If not, please message me and I'll take a look. So again, yeah, today we're gonna talk, inshallah, we're gonna talk about MLflow. MLflow is an open platform for machine learning lifecycle. And we're gonna explain what this means. The word is very packed, but inshallah we'll go through all of the components and the motivation behind this framework. I guess maybe a brief intro. Abdullah did give a fair intro, but I'll give a bit more. So yeah, I've been a systems engineer at Facebook for the past 3.5 years, working on mostly Apache Spark, which is another open source framework for distributed cluster computing framework, as well as data engineering, data science work, applied machine learning, and so on. So it's been very productive few years at Facebook, and certainly I learned a lot leaders in the field when it comes to the analytics, or when it comes to applied machine learning, or to open source tools. Facebook is one of the top contributors to a lot of open source frameworks, and I personally find this very intriguing and motivating. So I hope you guys will share this motivation and vision with me. All right, so inshallah, we're going to cover 4 topics. First, we'll be talking about the machine learning pipeline lifecycle, as well as the machine learning development challenges, like what are the top 3 issues that people face in development, either enterprise or at personal level. And then we can actually introduce MLflow and do a demo on it. Yeah, so I'm going to spend some time actually explaining the issues that the industry faces, or they used to face, and why MLflow emerges as a solution, and where it fits. All right, so first, yeah, let's talk about the machine learning pipeline lifecycle, or what does a simple pipeline look like in practice. So this is a simple chart for an abstract. It's an abstract chart for a typical machine learning pipeline at any enterprise. This one in particular came from a paper published by Facebook, but the same idea actually applies to any industry or any enterprise application. Pretty much every machine learning pipeline always, or machine learning in general, always starts with data. The assumption is data exists, or has been collected beforehand, and there is all, and then the question comes after, once you have sufficient data collection about any metric, like in this case, or you can take this example in particular, Facebook news feed. Some of you, as most of you are familiar with this application. Facebook injects ads in a lot of in their Facebook application or Instagram ads, and they, as part of the feedback loop, they collect information about the engagement of these ads. And by engagement, we're talking about a like or comment or share, or even just stopping the scroll and looking at the ad. These all count as engagements. So assuming that you have some infrastructure in place where you're logging these metrics, you're logging the likes, the comments, the engagements, shares, and whatnot. After some time, then you're trying to, the question comes, could you use this engagement data to try to predict which ads will become more engaging? Ideally, you would show ads only for people who are going to engage with it. So the step 1 of data collection is always predates and kind of the requirement for any pipeline. Now, once data is collected, then the first kind of data science work starts. Mostly in the feature engineering, practice. So raw data is on its own is not really useful. So it takes some sort of transformation to make it, to turn it into features, which can be actually used for training. Yeah, I'm not going to go deep into what features look like. This is another talk, but simply data to feature transformation is a data. It's called a feature engineering work, and it's very typical of data scientists to spend some time extracting features that you think they're useful, or that they assume they think there is promise behind it. Now, once features are collected, the third step, the obvious one, is training. Using picking a model architecture, trying different features and different parameters and so on, doing training. And training is also, well, it's not a singular step, but there's a lot of feedback going on. You train multiple models, try to improve and tweak until you get the best performance. And once you have a good performing model, then you ship it, and you actually use it for production, and that's called inference. So you could see this pipeline is split into 2 halves. There's online and offline. The online section on the right is the real time system. So when you have an inference, it's usually done at online level. So as someone is using the app, they are getting ads in real time. And so is the feedback collection. But the rest of the components, data collection, feature engineering, or training, these are done offline. Could be daily or weekly or monthly, as it suits the model. So as a high level, this is what a machine learning pipeline looks like. What I want to emphasize on here is the feedback loop. It starts from data and it ends with the predictions, but always goes back and use the new data and try to improve. And we'll explain why this is important. Now similar summary. So we just saw the feedback between data and deployment. This outer loop is very important to maintain a model performance that keeps up with the changes of people's behavior. This is the outer feedback loop. There is also another feedback loop that's internal, which concerns more data scientists or developers, which is going back between features and evaluation. This smaller loop in the middle. This loop is usually is a kind of a core feedback loop, and it's much faster. Like it's done at the iterations that happen here are much higher frequency, and it involves a lot of tweaking and testing and experimenting. And our focus will be actually more of this internal loop between feature engineering and evaluation or training. And we'll try to we'll try to explain why this loop matters a lot and why it's actually challenging a bit. So that now that we got an overview what a life cycle looks like, and from a high level, let's look into a few machine learning development challenges that people face, and then that's or at personal level. So first, okay, well, this chart may be a bit overwhelming, but actually this diagram came from a paper called Hidden Technical Debt in Machine Learning Systems, paper published in NeurIPS, in the NeurIPS conference by a team of Google engineers. What I want to highlight here is the middle section here. So you could see actually what this paper is trying to explain is that it's often the case that the core machine learning work, by core I mean we mean like the model algorithms, the algorithms that power the model training, and also a few more things, only make up a very small part of the overall picture. So we could actually see this ML code section or box. It's relatively small in size compared to the rest of the surrounding components. Like you could think data verification or collection. Collection is actually a big step that requires a lot of infrastructure, a lot of effort to do. Analysis is a big one. Monitoring is also a big step. Once you have a model, you ship it. Monitoring the performance of the model actually is very important too, to prevent users from either seeing the incompatible ads or being driven away from the service because the predictions you are making are very off. So what people think that the exciting part of machine learning is actually very small, like writing the model itself or the model code. The rest of components that surround the machine learning ecosystem are actually a lot of them, and they are a pain for pretty much every a pain to deal with or to manage. A lot of fragmentation. As you saw before, there are 5 segments in the machine learning life cycle. So a lot of toolings that serves every section. So it's fairly interconnected and fragmented. So that is an overview what machine learning is. It's not simply writing the pipeline code, but there is a lot more to it than just that. And we'll see why in a minute. All right, so I'm going to just summarize 3 machine learning or 3 challenges in development. A big one that we pretty much most of you maybe have faced. I personally used to face this a lot too, and I still do, which is the issue of reproducibility. You could always write this one pipeline using Keras or PyTorch or scikit-learn, and you will use some data, you train a model, get some results, but then you come next day or next week and you just restart the notebook again, and all of a sudden the model you actually that you end up with the second time performs differently. Could be worse, could be better. And you try to restart the model again, and you end up with different results every time. So model training is not well, usually it's not a deterministic process. So there are some variables, a lot of initial conditions or initial state conditions can be random, and that could lead to actually completely different models, especially let's say random forest trees or so. So it's really reproducing a model is actually often a challenge, which might lead to results being often inconsistent. Another part of the experimentation is parameter tuning. So a lot of pretty much every model that you work with will require some initial conditions or assumptions. Could be for a tree, the depth of the tree, even for deep learning, like what is it? Like a learning rate is one high parameter. It could be the number of hidden layers. So a lot of parameters that change between experiments, and it's often a pain to keep track of these, especially if you have a Python file or a Python script. You could use one variable, use one value for a variable, but then you also run a notebook, and you end up with a model, but then you try a different one. And it's hard to go back to the original one because you already tried something else. So these two issues are big. Yeah. Basically, reproducibility is often a challenging aspect of pipeline development. Because really, sometimes you want to go back and compare your results to something you tried last week. But oftentimes that you don't have access to that. So that's one big challenge that pretty much anyone who writes a pipeline deals with. Another one, model staleness. By model staleness, what I mean here is the model getting old. So maybe this could be clear if I contrast it with the software engineering. So with software, you could write a script or build a website or write a binary, and then you publish, and then and that's it. Maybe you could make updates and fixes and release the next one in the future. But in the meanwhile, the app will perform the same way until the new release is made or produced. But for machine learning, actually, that's not often the case. What happens is, even if you just make if you have picked the right model with the right data and you train a good model, you optimize it to the best parameters you could, the models on their own will actually get worse over time because the data that you use to train them are no longer fresh. They're no longer representative of the user behavior or the user actions. So often pipelines need to be always rerun or updated on daily or weekly basis to keep up with data freshness. As you recall from the first slide, we have this feedback loop. We have you log data and then you kick the training again. This loop is always pretty much continuous. It's continuously triggered, so you always end up with a model that's always up to date. And as an example of staleness, there's also from training sequences at Facebook. So some model like a news feed, I'll actually retrained again in the matter of minutes. Because as you recall, news feed is pretty much it could easily change in a matter of minutes. Maybe a new topic might show up, a new hashtag, or a new breaking news might take over. So you have to always be up to date and capture the latest trends there are. So a news feed model is actually then are trained very frequently. Search models also on the hours because of new terms. Language models like translation or summarization models are trained in a matter of weeks, days or weeks. Language is not changed that fast, but it's still you want to keep up with the latest slang or latest words that people are actually adding. Lastly, the face recognition models are the least trained ones. Maybe a matter of months. People's faces don't change as often Like the data itself does not change. The face itself is the same. So we don't have to train as much or as frequently. So that's one, yeah. But the common factor is there is always a loop. It's never the case where you train once and you forget. Pretty much have to keep updating the model. The question is how frequent. And that can range from minutes or hours to weeks or months. Another challenge, the third one, that's also maybe matters more for enterprise users or enterprise customers, which is the issue of going from development to production. So it's often easy that you could write a pipeline in Python or in a notebook or in a Python file, but actually putting that model into use, like for a case of inference, is another challenge, because you have to, first, the production environment is often different. It's not the same notebook you're using anymore. Also, a lot of performance aspects are start to matter. When development performance doesn't matter as much because it's there's no penalty for latency. But for production cases, if you are browsing an app or let's say Instagram or Facebook and it takes a second to load the new ad, that might lead for people actually leaving the app and actually not using it. So latency and performance matter a lot more for production than development, which means the environments are different. So that's often a challenge to design for both and try to minimize the differences between the two. So yeah, so that's basically just a recap of the three challenges we discussed. So yeah, it seems like the development is hard. Well, a lot of issues with development, and it used to be worse. It hasn't gotten better, and one reason is MLflow. So MLflow actually was conceived started by a startup or a company called Databricks, which one of the contributors to Spark. So in actually 2017, the MLflow was actually first released at the Spark Summit. I remember it was there in the conference. So the primary focus or the primary motivation behind MLflow is literally to address the development challenge we just mentioned. Let's talk more about MLflow and why and how it will help. So first thing, MLflow is a Python library, open source, with more than 100 contributors. The goal of it is to simplify few aspects of machine learning lifecycle. Machine learning lifecycle or pipeline lifecycle is actually, it's fairly large and extendable. There are 5 steps, but MLflow tries to capture and deal with the smaller feedback loop that we're going to see in a bit. The nice thing about MLflow is very extendable. It integrates with a lot of the frameworks that everyone uses: scikit-learn, PyTorch, TensorFlow. Has a good UI for tracking and visualizations. Became very popular in the last year and a half. Almost 1 million downloads. A lot of contributors to it. What does it come with? So there are a few components, and there is a 4th component that was actually just added to the framework. But the 3 main ones actually the tracking, projects, and modeling. So tracking probably was the one that maybe we're going to spend more time on today. But simply what tracking means here is simplifying the experimentation with pipelines. An experiment, or machine learning or not, involves a lot of bookkeeping and tracking of variables. So it's really easy to miss and lose track of the experiment, which might lead to inconsistent results or a failed job basically. So the better tracking of an experiment, the more likely you'll end up with a high fidelity result that you're more confident with. So that's the first module, the tracking project. There's also the projects one, which another utility of MLflow that allows any user to package their model into a platform agnostic format that you can ship and run across any other another environment. Talking about running locally or running in the cloud, like AWS, SageMaker, GCP, Azure ML. Like there are quite a few environments now, even for cloud too. Keeping things consistent, working across them is a challenge, and that's one of the things that MLflow tries to focus on. There's also the modeling one, which deals with the serving one. Once you trained and optimize the model, you want to serve it and containerize it. So that's another feature or another component that MLflow offers. Today we're going to focus actually more on tracking. It's one of the first. It was the most, I guess, important and the first actually component to be added to MLflow. So let's learn more about the tracking and why is it, what does it actually do. So before we go to the demo, we're going to just look at a few small things. So simply in a machine learning experiment, a few things that you track usually are, there are hyperparameters, key value pairs. For example, there's for the trees, there's the tree depth, number of iterations, learning rate. There are quite a lot of these. It could be number of hidden layers in a deep network, a deep neural network. So those are referred to hyperparameters. There's also metrics, which things that actually measure for every training iteration. So accuracy or recall or area of the curve, quite a few metrics that apply to different models. So these are referred to by metrics, which things that you use to compare models' performance against each other. Becomes very handy in the UI, which we're going to show in the demo. There's also artifacts. So essentially, once you train a model, you have a binary file that holds the weights or the encoding for the model. So that's one of the outputs. You have this binary file. You also have you could have some metadata, some visualizations, and others. We can look at these as well as the source code. So yeah, so basically you track the inputs, outputs, and also by product. So that's kind of what goes into an experiment. MLflow offers a tracking server, so we can actually we're gonna look at this in the demo. But basically, what MLflow gives you is an API interface that you can plug with any experiment to log the metrics you care for, and then visualize them and compare them later. And that could be, you could log from local experiments and save the results to some database in the cloud and visualize it. So very flexible and extendable. All right, so finally, before we go demo, yeah, we're gonna focus. So the component we just looked at is the MLflow tracking deals with simplifying this segment. So the ML lifecycle actually is very wide. It goes from data to deployment. But a lot of it's often painful enough to deal with the training and evaluation one. This feedback loop is very often the most demanding one from data scientists and users. Yeah, MLflow does not solve the issue of data management and data governance or data versioning. These are other big challenges. A lot of other products try to solve it. MLflow is not focused on the data one. Recently, they have expanded more to deployment one, so try to offer deployment model serving. So yeah, I guess there over time they're gonna try to cover more and more of this this life cycle. All right, finally, there's some information here. It's not really too actionable, but the size MLflow.org, as I mentioned, like almost 1 million downloads monthly. There's also a managed MLflow services. I think Databricks and Azure offers it. If you do want to install it and deal with it, you can always use the cloud version. All right, so then that we looked at the, I guess the theoretical part of this of the workshop. We're gonna go into a demo. So let me stop sharing and open the notebook. Yeah, I was going to mention 4 questions. You could please write. Okay, let me look at the questions. Maybe I could answer it. Yeah, we'll look at the questions at the end. I'm happy to answer all of them for sure. I actually want to spend a good time on them. But let me go. Yeah, let me go to the modeling section and do a demo. So we could. All right. Yeah, I see your questions. No, I can see them and we'll get to them in a bit. All right. All right, let me check this. I'm just going to share the screen and try to share the cursor so you guys can see it. All right, as you can see, yeah, I suppose you can see my screen. If you cannot see it, or if you have issues, it's too small, you can write in the messages, and I will adjust if I need to be. All right, so this is a notebook actually I worked on recently, and now this will be all published. The slides and the notebook will be published publicly, so you guys all can see it. And let me just I'm gonna go through and explain it, so we actually understand what we do here. So I'm using Google Colab notebooks, all based in the cloud. So let's go through this. So yeah, these sections are not really too important. So we have just a Google Drive mount, importing libraries, very standard things. And here's the data set. So first, actually, let's look at the data set, see what we are, what this demo is about. So yeah, this demo is actually about MLflow. But MLflow is a library for machine learning. So I cannot just demo MLflow on its own. We'll have to do some use some model and data and modeling, and then use MLflow on top to show how it helps with experimentation. So yeah, so pretty much 2/3 of this notebook is a normal machine learning modeling case. There's a few machine learning MLflow part of it, which we're going to explain. But yeah, so MLflow assumes you have a working machine learning training example, and it adds on top of it.
Hi, Abdulrahman. Can you just zoom in a bit more? I think.
Oh, sure. Yeah. You can tell me if it. Actually, I can zoom. Let me zoom in. I will zoom in further. Actually, but yeah, I certainly want this to be readable. Let me zoom in more.
Yeah, I think this is good. Yeah, thank you.
Okay. Yeah, thank you. I don't know. All right, I just switch my headphones. Okay. All right, so we continue. So yeah, this notebook is mostly it's a standard modeling pipeline, and there is the additional MLflow sections. We'll go through each. So the first thing we're going to go through is the data. So let me just explain what data set that I picked is. Some open data that I found on University of California Irvine's website. It's a bike sharing data set. So let me briefly explain what this is. So this data set has records of a bike sharing system. Think of a rentable bike rack. So there is, I think, a rack in Irvine or some, I don't know, I'm not sure which city is it, but it's a company that owns and rents bikes by the hour, and they collected data about their usage. So what the data has, they have a date, the season, the year, the month, time, whether it's a holiday or not, weekday or not. Also, they have weather information, what the weather was that hour, temperature, humidity, wind speed, and most importantly, this one is the number of total bikes rented. So they're tracking how many bikes they rented by the hour, and also tracking the environmental variables, and also temporal and environment. And the question is try to build a model that could predict how many bikes will be rented given the day and the weather conditions. So let me show an example of this data look like. Maybe it will be easier. So here I'm importing the data, just extracting it and loading it to a data frame. So here is what the data looks like. So simply, actually, let me show you what the cleaned up data is. Yeah, here we go. So this is the post cleaning. Let me just hide this for a second. So what the data looks like, yeah, this is what the data looks like. So season, so we have one. So that season is ranges from 0 to 3. So spring, fall, autumn, and winter. Year, 0 means 2012, 1 means 2013, so it's over 2 years. They explain this in their website. Month, 1 to 12. Hour of the day range from 0 to 23, so 24 hours. Also, there's some Boolean columns. So is it a holiday or not? What weekday is it? Is it a working day or not? Because you could have I guess holiday and working day are mutually exclusive. But you could have a Monday that's a holiday. So that's why they want to note it with a workday. Like some national holidays might fall into a weekday. So anyway, these are information about the day of the rental. There is a weather situation too. This ranges from 1 to 4, and they explain it here. So here are the numbers. So 1 means clear, 2 mist, 3 is light snow, 4 is heavy rain. So 1 is the best, 4 is the worst in terms of weather or biking. Temperature is normalized, and so there's also feels like temperature, and also humidity and wind. And finally, rented bikes. This is how many bikes they rented that hour. So if we take this in a row, for instance, this row is for season 1, which is fall, in 2012, January, in I guess there's 3 in the morning, and it's not a holiday. Weather was okay, temperature was fine. They rented 32 bikes that hour. That's what it means. So very fairly simple data set. Quite a lot of pipelines use it. And here are what the rows look like. So yeah, there were a handful of features, which is useful for modeling. We can do some simple data exploration. So we can plot I'm just plotting the total rented bikes by hour of the day. So we have 23 hours in the day. So you could tell maybe there's some people renting at midnight. You can see like in the morning, 7, 8 in the morning, the peak. And then we have some, later in the morning, where some people get to work, they stop renting. Then you have the afternoon, and probably 5 p.m. is another peak when people rent bikes again, and then it just declines until the end of the day. So seems very intuitive. People rent bikes, early in the morning before work, and also right after work. So that's one feature, the hour a day, and there are quite a lot of them. So the question is, try to build a model that estimates or models the number of bikes rented by all the features just mentioned. So now we have a data set. What we first want to do is obviously want to split the data into 2 sections. There is the training and testing. And there's also, I'm using the standard using standard functions to that. So 70-30 is the rule of thumb. So we have 30% of data used in, in testing and 70 in training. And here I'm defining the input and outputs. So X is the input for the training, which is everything except the output variable, which is the rented bikes. The output is what the predicted entity is the rented bikes. So yeah, using very simple scikit-learn terminology here. So we have a split. Here we have 14, almost actually quite a lot. 140K training samples, which is quite good. Now here is what MLflow starts. Now we have the data split. So now we're done with step one. Having data is collected, is cleaned up, pre-processed, organized. Inputs and outputs, and testing and training. So first that comes to mind here is, well, first thing we do is MLflow. First you designate an experiment. So you tell, well, this is an experiment called rented bikes. So MLflow now will know from now on, everything here will be about the rented bikes experiment. Very simple helpful methods. I'm not going to explain what these two, just very simple methods that, given a model, they extract some scores, like the root, mean, squares, error, very popular metric you capture from any score. There's explanation for these. There's also a cross-validation score. So when you train a model, you do not want to just use the segment of training for the score. You want to use the rest of training data to get an accurate measure of score. Which is here is referred by cross-validation. So let's explain what cross-validation is. But yeah, what these functions do, they just basically you give them a model and then a trained model, and they count or collect performance metrics about it, so we can compare it to others. Now we also have another helper method, which is logging to MLflow. So MLflow expects you to call it to log some metrics, and here what we're doing here, I'm saying, well, for every run I want to collect some metrics that I have in these two dictionaries, which we'll explain in a second. But basically here what these lines do, these lines log the parameters used. So I'm telling MLflow, log these parameters, please. And these parameters are actually listed right here. There's a number of estimators, there's a loss function, there's a learning rate and max depth. These are the most important ones that we care about. So MLflow, I'm just telling it to track these ones, and also I'm telling it to track metrics, which are the outputs or the scores. And here we have two scores, or two metrics. There's the root, mean, square, very popular, popular score used for benchmarking regression models. Also here I'm saving the model itself. We'll get to this. We'll see what this will do in a minute. But yeah, this code is fairly standard, and it's not special to this notebook. You can find it in the tutorial webpage. Anyway, so this is now we're getting we got this out of the way. Let's go to the parameters. And before I go to the parameters, I'm gonna make a small thing. So I'm using scikit-learn library, and I already decided that I picked a gradient boosting regressor. So it's a very powerful regression technique. So I'm using decision trees for regression and using a boosting technique for those. Now, there are a lot of models, a lot of techniques to do them. I already picked this one based on recommendations and prior experience. It's a fair question to say, well, which model to use and which not. Actually, there are guides online that you can follow, and it will tell you which model architecture should use. Should use linear regression, or should use decision trees, or others. By the way, for the sake of this demo, we already picked this model type. All right, so what's going on? So this section is where things actually get interesting. It's the most important section of this notebook. So what I'm doing here, let's look here. Look at these two dictionaries. So you have the parameters dictionary, which has, you can see it has, well, pretty much it's a fixed value parameters, number of estimators, pretty much using almost the default value, using default values for all of these. These are static variables, they don't change. What matters more is this one, parameters grid. So for every decision tree, there is a depth that you could choose that will affect the performance a lot. So what I'm trying to do here is I'm trying to, what I experiment with, my experiment would cover all these 3 or 4 different depths. I want to try 3 of them, 3, 4, and 5, and 6. At the same time, also I want to try different learning rates, which also affect the performance. I want to know which one is better or worse. It's hard to tell which one will be affecting the model positively or negatively. That's why the big questions or big challenges in machine learning today is, at least in the training section, is these hyperparameters, choosing the right hyperparameters, and no one really knows which parameters are the correct ones. So what you can do is set up experiments and then find the ones by experimentation. And we'll see how this MLflow will help us. So now here we're just generating the experiments. So we're trying every combination possible. So we have 3 and 4, so we have 12 experiments, 3 times 4. So here we define the model. We do a fit. So actually that's where the training section happens. We're printing something, printing some parameters. And then here is where we actually get the stats about the performance. These are the scores that are going to be used to compare the models across each other. And once we train, we get the training results, and then we log it to MLflow. And we'll see what this logging will look like. So I run this log. It takes a few minutes, fairly quick. And you can see a lot of iterations between these two. And you can see, well, this iteration had this loss ratio. This one had a different loss. So you can see this one was this run was actually better than the first one. And the third one was even better. The fourth one was worse, and so on and so forth. We don't have to try to decode these values. We're going to use MLflow for this. All right. So now that we did the training, we can look at the evaluation section. So okay, let me stop right here. And now I'm going to look at open the MLflow UI. So MLflow also opens a UI in the background you can access. So let's actually go and look at it. This is the MLflow website. So here is the MLflow I have for the experiments I just opened. So when I run this this cell here, this ran 12 experiments, and they all got logged to MLflow. And in the background they had MLflow running. So as I mentioned, MLflow comes with a nice UI, the one you're seeing here, which we're going to explore. So let's go through this a bit. Yeah, so experiments. So we have one experiment here, which is the rented by X1. I'm only doing one experiment today. It's one category of experiments. And here's what I'm doing. So I have these 12 experiments. And now let's look at these ones. So for each experiment, I have a start time. So these ran today. Each experiment has a few columns. So training, these are parameters I chose to log. So training size the same columns for each. Learning rate. Well, now we can see that learning rate is actually different for each one. And also, I think let me open the parameters. So there's more parameters than just this one. So I guess we can show the ones that we care about. So number of estimators. So I think the ones we cared about is learning rate and max depth. So let's just keep these. These are the ones that matter to us. Remember to go back here. These are the 2 parameters we actually experimented with. We had 12 experiments. So yeah, let's go back to the UI. So here is the value for the first parameter and the value for the second one. And here are the results for both. So we have 12 experiments and the results for both. And you can, so RMSE, that basically means the lower, that means the error in the model. So the lower the RMSE, the better. And the cross-validation one is stronger. It's has stronger coverage. So this is the metric we actually care about more than just a singular RMSE. So let me even hide the other one. So I'm going to go to metrics. I'm going to hide this RMSE. All right, now we have the inputs and the outputs. Now, actually, these are the numbers, the performance numbers I care about. And if I click here, actually, I can sort them by up to down. So the lower the value, the better. So what this tells me, the best model here is the one that had learning of 0.1 and depth of 6, which is 6 levels of a tree. It had the best, the lowest error out of all of them. And not only that, let's do even more things. Let's do a comparison between these two. Maybe look at the numbers alone is not easy, but let's do a click on compare and see what do we get here. All right, wow, so we get another UI. So actually it's quite full of things and it might look overwhelming, but let's spend a second maybe. So same data we saw, you just show it in a tabular format. So I have a start date and here's each one. So run one, we have training size, and you can see the highlighted ones are the ones that changed between different runs. And here are the results. So what matters to me the most is, as a developer, what is the relationship between learning rate and the error rate? So, well, there's a simple plot here we can do. We can use scatter plot. So let's compare that. Let's look at the learning rate and look at the cross-validation error. And we get this plot chart, this scatter plot here. Learning rate in the x-axis and the error in the y-axis. So it looks like, from what I can tell here, the higher the learning rate, the lower the error. And that's evident by these 4 dots. These 4 experiments, each dot is an experiment. It used the same learning rate, and they all had lower error rate than the rest. So it means the higher the learning rate, the better. So that's good. Let me look at the other variable now, which is the depth. All right, well, similarly, it looks like depth is inversely, well, it's also proportional, inversely proportional to error. So the higher the tree, the higher the tree, the more levels, the lower the error. So we can see this one, these ones here, they have the highest level, which is 6 levels. Also, they have the lowest error rate among all of them. Now we were looking at a lot of variables. Can we visualize all of them? We can also visualize them as a contour plot. Maybe make it easier. It's more like a 3D visualization. So we're plotting 2 variables, learning rate and max depth. These are the 2 variables we're playing with, and then we're going to compare the output. So from this one, we can look at this heat map. It looks like as we go higher in the x-axis, we get lower error, get a lighter shade of blue. And also, if you go higher in max depth, like even here, we even get a lower error rate. So maximizing learning rate and depth leads to a better model. That's pretty much as a conclusion we are getting. Let's look at the last one, this last plot, which might be a bit overwhelming, but this will explain what how the inputs actually affect output. So let me remove the stuff that does not matter. So these are not related. These parameters are not something we're actually experimenting with. All right, here we go. So let's take a second to dissect what this looks like. So what we're looking at is, well, we have this first parameter, which is the learning rate, and we have a line. A line kind of defines an experiment. So each line here is actually, you have 12 lines. 12, we can traverse 12 lines from like 1, this is 1, from here to here to the end. And also we have this one, blue one, all the way to the end. So we have 12 of these. But if I look at the output, just the validation, where is the lowest? So blue is the lowest. And if I look at the bottom here, where do these lines come from? Well, it looks like they all come from depth of 6. And the lines in depth of 6 seems to come from also higher, the highest learning rates. So if I traverse this line, which is the top one here, this one here, like 0.1 to 6, this first one. And also then you can see it's the same line that goes all the bottom. Maybe it's hard to see in my screen, but what this plot is trying to show is maximizing a learning rate and max depth leads to reduces the error the most. So that's one thing that actually we're able to tell from MLflow's experiment tracking. And if you go back to this one here, we can sort by error, and we can tell this is the best one. So what this tells us here, max depth and of 6 and length of 0 and 1 is the best. So I could, in theory, go here, and actually I can remove all the other values that I know are actually worse, like here. So now I'm using the correct variables. And that's kind of the results of the experiment. So that's one thing that MLflow helped with, the tracking the experiment. The last thing I was going to show is other thing that MLflow will keep track of. So we're visualizing trees, so we did something interesting. So there's feature importance, some visualization of the models we actually had. So we can tell you the hour of day is the most important feature of our prediction. There's another few. It's not going to go in detail of these charts. They're very standard. I guess they're not MLflow related, but more of modeling related. I'm also visualizing the tree here. The tree actually we're using. This is actually the tree that we picked for our model. But the thing I'm going to show you actually is an MLflow still. So let me go to an experiment. I'm going to pick this experiment and click on it, and it will actually zoom in and it will show me more information about that singular run. Same parameters I used, learning rate, the outputs. But the most interesting part actually is here, the artifacts. So MLflow keeps track of the output data and also visualization. So I don't know if you remember, there is a feature important chart. So I can actually understand easily what this model is about and compare it to others. So this is the feature importance chart for this model. I can also click on another chart here, solution. We can click on the decision tree itself, which is if you want to visualize the results and how you get, how you can traverse the outputs and inferences from this one. So MLflow is tracking all the variables actually in here. So yeah.
Abdulrahman? I'm afraid we're almost out of time.
Actually, I'm done with the demo. That's
okay.
That's actually the last one I was going to show. So yeah, I'm actually done for the demo part, and we'll go back to the questions that you guys answered. So let me stop sharing this. And as I mentioned, this will be all published. So don't worry about not seeing it.
Cool. Thank you, Abdulrahman, for this interesting talk. We'll take a few questions just for the Q&A part. So this question is, to avoid model staleness, do we need to retrain the model? Are there any standards regarding that part? Like how frequent and when to do it?
Yeah, so for the avoiding staleness, you can maybe open the slides quickly. So staleness is an issue that happens with it happens on its own, even without actually any interaction with data. So basically, staleness is a function of how fresh your data is. So if you do not retrain, your data will basically get stale. So the solution is to continuously retrain your model. Are there standards related to this in terms of frequency? So there are no set standards, but it's basically you want to maintain the same velocity as the data, how the data fundamentally changes. So when news feeds mentioned is done in minutes because news can be trending in minutes. Notice face recognition models are done in months or years because people's faces don't change that fast. So frequency depends on the data, the nature of data itself. So yeah, model staleness is avoided by retraining. Frequency is based on the nature. It's more data nature related. So I guess that's a question. I think the Akil's question.
Yeah. So the other question is how to deal with poisoning your output data.
So yeah, there's similar questions. How, for example, you keep Facebook sites to show or not based on similar like share. All right. So I guess poisoning. So poisoning sounds a bit more malicious or intentional, but let me put it in the way. So in the maybe share the slide actually. Hold on, open it. So if you remember the pre-processing, I'm gonna share the screen quickly. I'm just going to go back to this step here. So in terms of poisoning or decommissioning, so in the data pre-processing or like post, when you have log data, you usually do some kind of you still pre-process it, which means you apply some heuristic functions. Like there is, very simply you could tell, like for example, like maybe in the case of Facebook, if you have 1,000 likes, per hour from one user, you could easily, detect this anomaly and reject these logs. So basically, you can avoid anomaly, avoid the extreme data by doing some anomaly detections or anomaly corrections and avoidance, and also data conditioning. So you have some sets of mins and maxes for each feature that you expect, and you condition your data to. So it's a pre-training step. Before you train, you apply the preconditioning procedures, which is finding anomalies and removing them, mins and maxes. If someone likes a photo, like no human can make 1 million likes an hour. So we can always set a max and reject everything above like that. So yeah, there is always there's an expected set of values, and there's also extremes. You can also use the percentiles, like reject 1%, like the 99th percentile or above. You can assume as anomalous and reject it, and so on. So yeah, the question is, you deal with it statistically. MLflow does not really help with this part. It assumes the data is already cleaned and pre-processed. I guess, yeah, that's a question.
Okay.
The next one. I can read them myself. Do you want to read them, or should I read them myself?
We would like them announced to the audience. They can see them.
Yeah, I was going to read them myself, but you can read it too.
Okay. So this is a question regarding this slide, actually. Can you do feature selection training and etc. through the platform?
MLflow does not today directly help with that. So I think that when MLflow was released, 2017, so actually 2018. It was 2018 was released in June. The first thing actually tried to tackle is improving, just doing the tracking, experiment tracking. The parts just go in through in the notebook, which is more like training evaluation cycle. Features were not. Feature engineering were not something that MLflow helps with today. However, there are other libraries that do help with improving and making selection easy. There's an open source feature store, Python library that helps with synthesizing and generating features. So MLflow does not directly contribute to it, but you can integrate with you can do your feature engineering step before MLflow is invoked. It's fair, as mentioned, MLflow is fairly extendable, and it does not really assume a lot about your pipeline, so you can just integrate it in the sections where it matters or where you need it. So yeah.
Okay.
Similarly, like data versioning and conditioning is something that's not managed by MLflow. A lot of the pipeline is a lot of challenges in each of the sections. So MLflow is trying to focus on the very few, primarily training, evaluation, and deployment. Maybe in the future, I'm thinking the future is expanding to cover more of these. So not today, in the future, probably yes.
Cool. So if we do an experiment and rerun that experiment again, does MLflow guarantee the same results?
Well, so no, it will not necessarily guarantee the same results, because you could be using let's say if you use a random forest, if you retrain, likely you could be ending in different states. But what MLflow will help you with, it will track all the inputs and outputs of that one. So let's say it will not prevent, so MLflow in itself will not prevent indeterministic models, but actually it can help you make them deterministic. What I mean by this is MLflow can track, let's say, the seeding numbers that you use for your random forest tree. So if you use the same seed, you could end up the same tree every time. So MLflow will help you track these numbers and then recall them in the future. So you're always using the parameters that will ensure you you end up with the same tree. So let's say MLflow enables you to track the right metrics that allows you to be deterministic. That's kind of the right answer. But MLflow on its own would not, if you just, if you import it, it will not really make your model deterministic. You have to integrate, you have to kind of track the models. And if you track all the inputs that you have from a model, then you will end up with a deterministic, reproducible model. So yeah, the answer is yes, if you do the integrations.
This is a question. So I understand that MLflow is used to maintain and document the ML pipeline. Can it be extended to automate some stages of it?
Yes. Well, so the automation part will, so deployment, for instance, it could help with packaging and creating containers for inference. I guess this part we didn't cover today, but it's one of the other three components of MLflow. But the answer is partially yes. But to automate the life cycle, the complete one, different tools are used. In particular, there's another popular tool also, Apache Airflow. Airflow actually is more of the automation tool. It's not machine learning specific, it's very agnostic. But MLflow used with MLflow, because Airflow and MLflow used together, you can automate the life cycle and also track experiments. So each component does one thing, and these two frameworks can help supplement each other. So yeah, so automation partially for the deployment, but to deploy the whole section, which is data extraction, features, deployment, and training, like actually running MLflow itself, this is done by another service. Look up Airflow. It's another popular open source framework that does exactly what you just mentioned.
Exciting. So I think this will be the last question. Are you planning another webinar about MLflow project?
We could do one. I mean, I'm happy to do another one, I guess, and deployment and inference. I guess we could, I'm happy to organize something, in next month. More of deployment evaluation demo, I guess. Yeah, I'm happy to.
Cool. So I guess
so that's our time. I might forward the rest of the questions to you, Abdulrahman, and we might post them on Meetup.
Yeah, actually answer on the Meetup page or on Twitter. I'm always happy to.
Okay.
Provide answers for those questions. But yeah, there are a lot of good ones I can see in the page here, but I'm sure we'll get to answer those in offline. Yeah,
thank you, Abdulrahman. And thank you, attendees. It's been
thanks everyone. It's been a pleasure. I enjoyed talking about this project and looking forward to continuing this one in the future. Yeah.
Thank you.
All right, assalamu alaikum.